Good morning, everybody. Thank you for joining us this morning. I want to extend a warm welcome to our folks at the centers who are watching us and taking time out of your day. I think you're going to be very pleased with the topic that you're going to hear about today. This is our first aeronautics seminar series, We intend to have these on a regular basis. Our intent is to cover technical topics and go into depth in areas of interest, and I think this is going to be very exciting. So I don't want to spend much time up here because I want to give time to our illustrious speakers today, so I'm just going to introduce them. Dr. Irving Statler and Dr. Ashok Srivastava. Both of them are from Ames Research Center, and they're going to be talking about recent data mining advances of aviation safety data. This is a really interesting topic. It's one that I've taken a personal interest in, and I think you're all going to enjoy this talk today. So without any further ado, let me introduce you to both of our illustrious speakers. Thanks. Irv?
Good morning. It's a great pleasure and an honor to be invited for Dr. Srivastava and myself to be invited by Dr. Porter to give the first of the ARMD technical seminars. Dr. Srivastava is going to be telling you about some advances we've made in the capabilities to extract information from diverse data sources. The stimulus for this work has been some interest from the aviation community, and it's been supported under the ARMD Aviation Safety Program. However, as you will hear, the tools that we have invented have wider application. The U.S. air transportation system is the safest mode of travel, at least as far as the United States is concerned. However, the current low rate of fatal accidents will not be acceptable with the expanded air traffic that is expected and projected for the next decade. May I have the next slide, please? And so the aviation community has recognized that it needs to progress from its current dependence on reaction to the last accident. Next slide, please. May I have the next slide? And take a more prognostic approach that entails monitoring the system continuously to identify any events or trends that could compromise safety, evaluate the operational significance of these events, identify the causal factors, and the probabilities of the frequencies of the confluence of these causal factors so that they can formulate the most appropriate intervention and develop an implementation strategy that includes provision for monitoring the system continuously to measure the efficacies of their interventions. This is a proactive management of risk. May I have the next slide, please? And so the aviation community, while they're very concerned about protection of the data that they have behind their firewalls in the airlines, are eager to share information but need to protect their sensitive data, have established the voluntary aviation safety information sharing process as an acceptable way in which to comply with current information sharing requirements and yet protect the anonymity of the sources of the data. And the FAA has created the Voluntary Safety Information Sharing Aviation Rulemaking Committee, which is an advisory group to the FAA on the rules that should be made about sharing information. Upon the request of the industry and the FAA, NASA undertook a demonstration of the capability to develop a distributed national archives that would meet the conditions laid down by the VASIP and would operate under the rules of engagement established by the VASIS ARC. May I have the next slide, please? Well, the status of these national archives, and there are two of them in operation now. One of them is a distributed national archive of the FOQA data, or the Flight Operational Quality Assurance data, which are flight recorded data, quantitative flight recorded data, operating in parallel with the crash box that you're all familiar with access to up to 3,000 parameters on some of the modern aircraft. The archive now has 700,000 flights of, as I said, up to 3,000 parameters per flight, each of which is recorded at the rate of up to 8 times per second. So our current database, archive distributed database, is of the order of a half a terabyte and is increasing at the rate of 60 to 70 gigabytes per month from the 8 airlines that have agreed to participate in this demonstration. The other archive is a distributed national archive of the ASAP reports, or the Aviation Safety Action Program reports. These are the incident reports that are provided by the pilots whenever they have encountered an event or an incident that they consider to be of safety value. The database here is still small. We have a total of 10,000 reports at the moment, and we're adding about 1,000 events per year. An event is not equivalent to a report. There are about 1.2 reports per event because there may be multiple reports on a single event. And these are now from 6 participating airlines. And in fact, we have used these archives to do a study with the VASIS ARC working group on ground proximity warning system alerts taken from a national perspective across air carriers. May I have the next slide, please? These are the air carriers that have signed up to participate with us in this demonstration mode. At each of these air carriers, there is installed a NASA server. And the data, de-identified data, flows through a one-directional wall through the door through the firewall into the NASA server. But no data ever leave the premises of their owner. A query emanates from the center at Ames out to the various nodes. The analyses are performed at the servers at the nodes. So the analytical capabilities exist at the servers, and only the results of the analyses are sent back over to the secure network to be aggregated at the central site at Ames. 7 very good, 9 by the end of this month, carriers have been participating, but this is still only a relatively small sample of the full population, and therefore it affects the statistics with regard to bias and confidence. And so the success we've achieved now brings us new challenges. May I have the next slide, please? We have to enlarge the database. We have to need new additional airlines so that we can be more representative of the full population. And the aim is to add 10 new airlines over the next 2 years. In addition, it needs to be expanded to other data sources. These have been great choices. We've started with a key data in the flight recorded data that gives us a set of quantitative data. And at the same time, we've started with the textual reports from the ASAP data. So we've had challenges from both the textual side and the numerical side. So now we need to expand those to other data sources to get the total picture. For example, we have the airborne side, but we have yet to see what the ground has to say from the air traffic controller's side, from the air traffic radar traffic data, and from the controller's ASAP-like reports. maybe even their voice. In addition, we need to be able to enhance the capabilities because currently we interrogate the systems for prescribed events, identified prescribed events. What we need to be able to do, what we like to be able to do, is to monitor the system automatically, continuously, identify any events that could be compromise the safety of the system, investigate all the rest of the data for evidence related to that event, and then bring it all to the attention of the safety analysts. Next slide, please. And now it's a great pleasure for me to introduce my colleague, Dr. Ashok Srivastava, excuse me, Ashok, I knew I'd mess it up, who will tell you how he's going to cope with these challenges I've laid upon him.
Thanks everybody for coming this morning here at NASA headquarters, as well as all of the people that are out at the NASA centers. It's really a privilege for me to be able to speak to all of you about a topic that I find very interesting myself. I hope you'll find it interesting as well. But also because, as you heard Irv describing, there is a significant amount of data that is accruing in these national archives, and we'd like to be able to understand what's in that data. In fact, I'm the leader of the Intelligent Data Understanding Group at NASA Ames Research Center, and what we try to do is develop algorithms that will understand data from all sorts of sources. Today we're talking about aeronautics sources, but we've also done work with space science data, with earth science data, with all sorts of data sets. The hope is that when we learn something in one domain, maybe it can be transferred to another domain. Next slide, please. So I couldn't be here if it weren't for the hard work of a lot of people back at NASA Ames, as well as through the larger NASA community. Specifically, I'd like to recognize Dr. Statler for really giving me the opportunity to explore new technologies in this important domain. It's a very rare honor and actually a very rare privilege these days to be able to take technology and apply it to such pressing problems. And so I really would like to recognize him for that help. I'd also like to recognize the members of my team at NASA Ames, and they're listed up there. Each one of these people is either a NASA employee or a contractor for NASA, or as we like to have many students, PhD students, master's students. We all try to bring them together so that we can come up with a good, solid strategy for addressing some of these problems. Next slide, please. So we also need to recognize the key programs that are funding us, because without that, of course, we would not be able to have any success in any of these domains. And primarily, I'd like to recognize the Aviation Safety Program, which has been providing us with funding for a number of years to develop these algorithms. So it has been kind of the cornerstone of a lot of our activities. The NESC, NASA Engineering and Safety Center, has also provided us with funding for text mining work, which I'll be discussing today. ESMD, Exploration Technology Development Program, and the Shuttle Program have provided us with funds as well as necessary expertise in order for us to understand and analyze data. You know, when you get into the business of understanding and analyzing data, you can't do it by yourself. You have to have a domain expert with you, hand in hand, working together so that you can come up with an understanding of what is going on in that data. So it's really a collaborative effort, and we're delighted to have support in that manner from the Shuttle program. And finally, I'd like to recognize the Science Mission Directorate AASRP program, which has kindly donated, given us money so that we can also develop some of our virtual sensors technology. So next slide, please. So today I'm going to take you through three topic areas I hope that you find interesting. The first one is categorizing and detecting anomalies described in the safety documents. So what you need to imagine here is that somebody hands you, let's say, 100,000 reports and says, can you tell me which anomaly categories these things fall into? So you may feel ambitious and sit down and start flipping through them, reading them and noting down, you know, I think this is a runway incursion. Maybe this one is due to pilot fatigue and so forth. You could do that. But somehow that may not be as efficient as one might hope in today's technological age. We also talk about describe detecting anomalies, recurring anomalies. And these are the idea, again, you're handed 100,000 reports and somebody says, are there any trends of anomalies in this data? That's a good question. Is there something that keeps on happening with the system again and again and again that is being reported about, but we just don't know about it because we, as a human being, at least I, can't read 100,000 reports and make sense out of it? Can we devise a tool that could help us with that? So that's the first part of the talk. The second part of the talk is quite interesting. I think it's about detecting anomalies in cockpit switching sequences. So here what you need to imagine is that you've got a repository of data, let's say again 10,000 flights or 100,000 flights, and those data sets are composed of discrete as well as continuous parameters. Now what you want to do is build an algorithm that would look through all of the discrete parameters that are recordings of the cockpit switches inside the aircraft, look through all of those flights and determine whether or not a particular flight or a small subset of flights is anomalous or not. That's the question that we're trying to answer here. So to answer that question, we rely on some technology from bioinformatics and from machine learning there. The third area that I'd like to speak to you about is detecting shuttle wing heating anomalies, and if time permits, I can discuss some work that we've done on detecting anomalies in the space shuttle main engine. So there we'll get a little bit of flavor for some technologies that we've developed for the space programs that we believe might be of some benefit here in the aeronautics domain. Next slide, please. So take a moment and read this report. I'll read it to you for those of you that may not be able to see all the words. Just prior to touchdown, LAX Tower told us to go around because of the aircraft in front of us. Both the co-pilot and I, however, understood Tower to say, cleared to land, aircraft on the runway. Since the aircraft in front of us was clear of the runway and we both misunderstood Tower's radio call and considered it an advisory, we landed, ... So here we have a pilot, presumably, giving a narrative of what he or she saw happening in the cockpit, bringing that airplane down for a safe landing, and the pilot chose to send in a report to the ASRS system. This is the Aviation Safety Reporting System. He or she chose to send that report in so that at NASA we would know what happened. We can probably use that for some purpose. Next slide, please. Now, there are many purposes that one could use such a report for. Today I'm going to be speaking about the purpose of automatically categorizing these kinds of data. So on the left-hand side of the chart, you have that report again. And it's in free-form text, however the pilot wrote it. And the question is, which anomaly category does it go into? It turns out that ASRS has about 60 categories. DNAA has about 32 main categories. And so the question is, can you map it from one to the other? So when I was putting the slide together, I said, aha, that looks like a fumes category to me. Well, that's really not the case, obviously. There's no mention of fumes, but I'm not an expert. I might have made that mistake. Looks like a runway incursion. Maybe it could be, maybe not. Let's flip to the next slide and see what happens. Well, fortunately for me, I have experts that I can consult, and I talked to one of them, and I showed him this report, and I said, where does this report end up? And he found 4 categories that it goes into. The first one being non-adherence to ATC clearance. The second one, runway incursion. The third one, landing without a clearance. And the fourth one, ground encounter less severe. So now you can see that the expert looked at this report and he came up with a categorization that I think is quite reasonable. The question is, can you make a computer do this? And if so, how are you going to go about doing it? When you start doing searches on the internet using your favorite search engine, you're going to see that people use things like natural language processing, people use things like statistical methods, some people use machine learning methods, some people use data mining methods. The question is, though, what should you do, and specifically, how much is it going to cost to do that, and what kind of an answer are you going to get out? So we've had the good fortune for the last period of time to actually conduct such a study, and I'm going to describe the results of that to you in the next few slides. Next slide, please. So again, we've got a classification problem on our hand for those of you remembering your statistics classes. The idea here is that you've got reports and you want to map it into M of N categories. N here is about 60 categories. M in the previous case was 4. You might have more categories. Some reports might go into many more categories, like 12. 15 categories. Other reports might go into only one category, like security, for instance. If there's a security issue, probably that's all you need to say. It's a security issue. So the question is, can you build an algorithm that will take such data and map it into M of n categories? Next slide, please. Now, we've taken a data mining approach to address this question, and we're actually going to leverage some results from natural language processing. And I'm going to show you how NLP, natural language processing, and the data mining results relate to each other. So let's take a look at the way we represent the data to the algorithm, because this is key. The way you represent the data to the algorithm can determine whether or not the algorithm is successful or not. We've chosen a very standard representation of the data, which is called a bag of words matrix. This is not a magic matrix. All it says is that each row in the matrix corresponds to a document, and the columns correspond to the union of all of the terms in all of the documents. So what that means is that if you've got, let's say, 30,000 documents, just for argument's sake, and you count up all of the unique words there, you're going to get, for ASRS, about 40,000 dimensions, 40,000 terms. 40,000 unique terms are going to show up there. So this is a really big matrix, 30,000 rows and 40,000 columns. Now, we'd like to use this matrix in order to analyze it, in order to do that categorization. So this is the approach that we're taking. Let me point out here that you can augment this matrix with other information. For example, if you run a natural language processing software on it to extract concepts out of that data, concept might be the concept of a runway incursion or concept of fatigue, pilot fatigue. If you run specific software on it and pull out, say, aha, you know, this document has specific information about pilot fatigue. Let me note that down. Well, all that corresponds to is adding a specific column, a new column to this data set, so the dimensionality of the problem can grow. Next slide, please. So again, hearkening back to basic statistics and some computer science, you'll remember that there are many ways of addressing such a problem. Linear discriminant analysis is a popular method for taking data and mapping it into categories. This was done by Fisher many, many years ago. Logistic regression is another very popular method. Neural networks, most people have heard of them. They're amazing gadgets. They're amazing pieces of software, and they can be used for this as well. Decision trees also have become very popular for these kinds of activities. I'm going to talk to you about another set of algorithms called kernel methods. In machine learning, if you go to your, back to your desktop and do some searches on kernel methods, you'll see that about 10, 15 years ago, these methods started to take hold in the machine learning community because of their power and of their ability to deal with high-dimensional data. And if you think about it, we're really dealing with high-dimensional data here. 40,000 is a lot of dimensions to deal with, and when you start augmenting it with more information from NLP technologies, all it does is it increases the dimensionality. So the kernel methods give you a method of dealing with this data in very, very simple forms. And I'm going to show you on a toy example how that works. So let me describe to you a little bit difference between what's at the top of the chart and the bottom of the chart. The standard methods, many of them assume linearity. And for those of you thinking about it, you'll realize that, gee, maybe it's not a linear relationship. Maybe you can't just draw one straight line in the data space and separate the two categories from each other. That actually does tend to happen a lot. You could also find that it doesn't work well on high-dimensional data. Well, with the kernel methods, we find that in our examples, at least, they do work quite well, and they actually produce highly nonlinear models. But the way these models are built is very clever, in my opinion. Let's move to the next slide. So here's a little toy problem for you. And it's supposed to illustrate how kernel methods work. Now, let's not mistake that this is not the way documents appear in 2 dimensions or in 40,000 dimensions. It's just a Gedanken experiment that I'm trying to take you through so that you develop a little bit of intuition about how kernel methods work. So here's the problem. Gazing at that picture, figure out how to separate the cloud of points on the inside from the ring of points on the outside. So if you take a look at it, you'll see that it's probably quite easy. You just draw a ring around the inside points and you can do the separation. No big deal, right? Well, get a computer algorithm to do it and then we'll talk. Let's switch to the next slide. Now what you've got to keep in mind is that 40,000 dimensions is really what we're dealing with, not 2. So here I fired up my software package, MATLAB in this case, and I ran logistic regression, and it did what one would expect. It drew a straight line through that cloud of points. The red points is called one category, and the blue points is the other category. it didn't work so well. It's actually a reasonable classification of the data, but it actually is not what I wanted to have happen. So now I run neural network software, and I get the classification on the upper right-hand side of the screen. Well, this is another segmentation of the data, another way to classify it, but it's really, again, not what I was looking for. I take a decision tree, run it on that data, and it is more like what I'm looking for. That cloud of points on the inside is actually well separated from the ring on the outside, and a large neural network works similarly. So it gives you an idea of how these algorithms work on admittedly a very simple problem. But I'm going to show you now what a kernel does, and it's really quite amazing. Let's flip to the next slide. What kernel methods do is find the global optimum solution given a set of hyperparameters. Hyperparameters are basically little dials that you set on the algorithm that give the algorithm kind of a baseline of where to start from. And from there, it does a convex search. What that means is that it will find a single minimum, and it'll do it quickly. This is different than what you would find in other sorts of models. Neural networks, for instance, do work very well, as we saw in the last example, but they tend to find local minima. Frankly, sometimes that's not a problem, but for some applications, it actually is an issue. Let's flip to the next slide. So one of the most famous examples of kernel methods is called an SVM, support vector machine. And this algorithm, so far as I recall, came out about 10 or 15 years ago by a gentleman named Vladimir Vapnik, who had a quite brilliant, in my opinion, insight into the way one could solve these problems. So if you think about that 40,000 dimensional data space that I was describing earlier, most people, frankly myself included, first reaction is to say, you know, the best thing to do is reduce the dimensionality of that problem. 40,000 is way too big, let's make it 10. And so you do some sort of an analysis. You might do principal components analysis. You might do some other sort of dimensionality reduction to cut down the dimension. Well, what support vector machines do is actually quite different. Here you start off with p-dimensional data. Again, p is about 40,000 dimensions. And you create an operator, which I'm calling phi here, that takes that data from 40,000 dimensions, and instead of driving it down to lower dimensions, it explodes it into even higher dimensionality. So it could actually go into an infinite dimensional space, an infinite dimensional Hilbert space. Now, in that extremely high, potentially infinite dimensional space, you draw a straight line. And that straight line is constructed in such a way that it separates, maximally separates, the red dots from the blue dots. So take a look at the chart the picture that I have at the bottom of this chart. And what you're going to see is that in the data space, we have red dots and blue dots, and it's kind of hard to figure out how to draw a straight line through that to separate them. In fact, it's not possible. But using the operator phi in this higher dimensional space, again, this is a cartoon, but in a higher dimensional space, you could imagine that somehow it would be possible to draw a straight line through it. And that's exactly what we try to do. That's the idea of a support vector machine. So let's see what happens on our toy data set. Let's move to the next slide, please. So we start again with that cloud of points that I described earlier, and I've labeled the axis A and B, so it's 2 dimensions. And I hand-constructed a phi. And the phi is basically a quadratic form, right? A squared, square root of 2ab, and b squared. So it's a quadratic. Now, you take A and B and you map it through phi and you plot it and you get 3 dimensions out, right? Because phi is a 3-dimensional operator. Now, if you look closely at the chart, I hope you can see that there's a ring and then there's a cloud of points. And in fact, if you look at a 2-dimensional projection of that, you can draw a straight line between these two things. And so this is the idea of what happens in a kernel. In a kernel, the data is projected from the low-dimensional space, in this case 40,000, to a very high-dimensional space, in this case an infinite-dimensional space, the case that I'll describe to you in a moment. Then you draw a straight line through it, and somehow you're able to do the separation. Let's move to the next slide. Now, when I say infinite dimensional, some of you might be thinking, gee, that sounds like a lot of computational time. In fact, when I heard about this first, I thought that that's going to be very expensive to execute on a computer. It turns out, though, that there's something called the kernel trick. And what this does is it exploits the mathematics of inner product spaces. And instead of operating on phi directly, you operate on a kernel mapping called K. K is a quantity that measures the similarity between 2 documents in this case. I've chosen to use the radial basis function kernel that's depicted here. It's basically an exponentiation of the difference of the norm between two vectors. And what this does is it implicitly assumes, I should say, induces an infinite dimensional feature space. So phi is infinite dimensional, but I never have to calculate it. All I have to do is calculate k. So I take two document vectors. These are 40,000 dimensions. I take the difference, I square it, and then I divide it by 2 sigma, and sigma is a hyperparameter. I divide by 2 sigma squared, exponentiate it, and I get a single number out, right? But when you do that, you have implicitly induced an infinite dimensional Hilbert space. Let's move to the next slide. Now, when you do that, what happens is that that infinite dimensional Hilbert space, you draw a straight line through it, and you do a certain optimization procedure that happens to be convex. I can't get into that right now. And then you find the global minimum. We have developed a system at Ames which we call Mariana, which, for those of you remembering, there's the deepest trench in the Pacific Ocean is called Mariana. It's called the Mariana Trench. I think it's 6 or 7 miles deep. And if you think about it, if you took a lead weight and dropped it right above that trench, it's going to make its way, hopefully, to the bottom of that trench. It will find the global minimum. Our system does something similar. It finds the global minimum, so we thought that Mariana was a suitable name for this algorithm. So what it does is it finds a set of hyperparameters using Markov chain Monte Carlo techniques, and then it finds the global minimum, and hopefully it does a good classification. That has yet to be proven. I'll hopefully show you that to you in the next few slides. I'd like to switch now a little bit and talk to you about natural language processing, because this is an area that we have previously used in this program in order to understand some aviation data. I want to give you a little bit of background because it's going to be helpful for the next few slides. So NLP, as it's called, is a technique that is based on the use, at least in our implementation, based on the use of handcrafted key rules. So what this means is that expert or experts sit down and think about what sort of rules can we divine in order to capture certain concepts that are represented in documents. So I came up with a couple of rules. These aren't necessarily the best ones, but it gives you an idea of how this might work. So pilot fatigue, clearly that's an area of interest to safety. So I'd say, let's search for the word fatigue. Let's search for tired. Let's search for phrases like the last leg of an X-day trip, where X is an unknown. Sleepy. You can think of your own words. You type all of those into a computer, probably using something like a fancier search engine or a regular Express and search software, and it'll go through and it'll find all those documents. That's not surprising. And that seems to be a good thing. It seems like it would really capture good information that you've got. And it really does. But the problem is that it's really hard for at least me to sit down and dream up all the different ways that people can think of saying they're tired. If you talk to my daughter, she thinks of a new way every day. Let's move to the next slide. So let's compare NLP to data mining. Well, on the left-hand side, we've got NLP. Clearly, it's very precise, right? That means that if you search for security and you find a document that says security on it, certainly it's a security document. So it's very precise. It requires, though, at least in our implementation, large handcrafted rule bases. So you've got to sit down and do it. Now, there are ways of expediting the process, no doubt, but still, something requires that level of work. It's therefore, in my opinion, at least very expensive to conduct such studies. Now, data mining, on the other hand, which is kind of the world that I come from, is very different. We deal with very imprecise representation of the data. It's that bag of words matrix, right? So I've destroyed all context, I've destroyed all semantics, I've destroyed everything, the author's viewpoint, you name it, I've destroyed it. All I'm left with basically is word frequencies. Now, it's inexpensive, it's cheap to do it this way. Now, the hope is that somehow we can reconcile these two things and get a good answer out. What we actually do is we take NLP outputs and we feed it back into an SVM and then do classification. So the question is, did we have to do that or not? Can we just go straight with the raw text? Let's move to the next slide. So this chart shows you the unoptimized SVM. So this is not running Mariana. This is when you go to your favorite search engine, you download the first SVM software that you see, you hit go, you wait, and you get an answer out. You'll probably get something like this. And it happens to be the red diamonds at the top of the chart. And all the other algorithms that we've run here, which include decision trees, random forest, logistic regression, and linear discriminant analysis, all of the other ones show up below that top curve. And so what that means is that they have less accuracy. They're lesser quality classifiers for this data set than the support vector machine. So that tells you, well, gee, maybe something's working here. Maybe that infinite dimensional space is helping us out. Maybe we're actually doing a good job at classification. I would say, in fact, for this case, 51 categories were working pretty well. Only 8 times out of 51 does our algorithm do worse than one of the other algorithms using NLP technology. And what I'd like to say further about that is that you'll notice that the stability of the SVM algorithm is actually quite high. Let's move to the next slide. Now the question is, as I put forward, did we really need to invest in that NLP technology? How did it help us? So we ran Mariana against the standard SVM software that you might find off the internet, and look what we got. The stars and the red dots are pretty much on top of each other, right? So that means that basically, without going through all that investment of writing the rules, we're able to use Mariana, and we're able to get a pretty good answer. So that was very encouraging. But then look at the right-hand side of the chart. And what you're going to see here is that the yellow stars are actually up at the top. Even in these categories where we were having a hard time with the support vector machine, and frankly with all of the other algorithms, here Mariana is pulling ahead. Here we're finding the global minimum better. Here we're actually getting a good solution. So this was very encouraging for us. We've done other studies to show that the median the median true positive rate for this classifier across 23 categories is about 90%. And the median false positive rate is about 10%. So that gives us, again, good feeling that this algorithm is working and Mariana is doing its job. Let's move to the next slide. So what have we accomplished? What are our innovations? Well, using a Markov chain Monte Carlo technique, which I haven't described to you, but suffice it to say it's a method from statistics that allows you to do search for parameters. Using that technique, we're actually able to find really good parameters, and once we find those parameters, we're able to do good classifications consistently across 51 categories of ASRS, as I demonstrated before. Mariana performs as well or better than the SVM built using NLP technologies, but without the overhead, which is good news, because now I don't feel like I have to invest time and money and effort in building those sorts of rules to extract that meaning out. What I feel makes a lot of sense is to invest in making Mariana, a very generic system, work well. So we've demonstrated on text here, but we can also demonstrate it in science programs. We can demonstrate it on space programs. We can start to fold it out and start using it in other areas of NASA, and that's really what we would like to do with Mariana, as well as with the other algorithms that we've shown here. We also developed some nice noise reduction capabilities, which basically, if you remember this theory of signal-to-noise ratio, you want to improve the signal and reduce the noise. And we developed a certain technique to do that that actually worked to reduce the false positive rate by as much as 30%. So we're delighted by that because now we have a consolidated system that can ingest data, these text reports, pass it through, classify it, reduce noise, and get a pretty good answer, at least for the ASRS reports. We're investigating how well this works on the ASAP reports that Irv mentioned earlier, and it turns out that our studies are indicating that it works quite well there too. We're also dealing with the DNAA categories, the Distributed National ASAP Archive categories that have been identified, and it's doing quite well there too. So I'd like to move to the next slide now and talk to you about a related problem. It's not exactly the same problem as what I was describing before. Here again, imagine that you're given 100,000 reports and somebody says, quickly please, find recurring anomalies in this data set. Tell me what's going on with my system. And by the way, my system's been around for, let's say, 20 years. So how are you going to go about doing that problem? Let's move to the next slide. Well, these reports do not have an anomaly category associated with them, and you might have, as I said, several 100,000 of these reports. And we want to do some trending on it. So what trending means is that we want to find an anomaly and see whether or not it's changing over time and so forth. Now, if you go to your, again, standard search engine and you say let's try and solve this problem, probably you'll find out that clustering is a statistical or machine learning technique, a data mining technique, that is used to solve problems like this. But you know what happens is that when you run clustering algorithms by themselves, you don't really get a recurring anomaly out. What you get is similar documents, which is kind of the same thing, but really not what you're looking for. So what we do is we do clustering, but on top of that we do what we call content-based search. So we actually look in the documents, see what the documents are saying, and then see if they're referencing other documents, and we take advantage of that. I'll show you that in the next slide, please. So the definition of recurring anomalies, by the way, that we're using is given to us by the NASA Engineering Safety Center, and it is that recurring failure described in text reports. So we're not looking at continuous or discrete data here, we're just looking at the text reports, and these are problems that may cross traditional system boundaries. So I've got a picture of the Space Shuttle main engine here, the SSME. So you could imagine that some sorts of problems that may be reported in the SSME may actually have relations to reports that are happening in the external fuel tank or other parts of the SSME environment. And so we would like to be able to look across system boundaries. What that implicitly implies is that we're going to have to be able to deal with multiple data sets, multiple databases, not just one database. Let's move to the next slide. So how do we do it? I'm going to take you through 4 charts here that is going to show you step by step the procedure that we follow to search for recurring anomalies. We're going to start again with that term document matrix that I described earlier, the bag of words matrix. Remember, this is about 40,000 dimensions and about 30,000 rows. And we're going to calculate the similarity between all vectors in that space. And the way we calculate the similarity is that we use the cosine measure of similarity. And those of you familiar with the idea from information retrieval will realize that, in fact, in information retrieval, in that science, they use the cosine similarity in order to compute the similarity between 2 documents. So you might remember that if you have 2 points in a p-dimensional space, if you want to compute the angle between those 2 points, you can use the formula that's on the screen here. That gives you the cosine of the angle, actually, and then you can manipulate that. So it tells you how similar are these 2 documents. Next slide, please. Now, once you've got the similarity, what you do is something called agglomerative clustering, and this is not a big deal. All it says is that if 2 documents are really similar to each other, let's say their similarity score is 0.9, then lump them together. And you keep on doing that until you've built basically a tree. Now, what you lumped together at the very beginning of that procedure is one definition of a recurring anomaly. It's a clustering definition of a recurring anomaly. And you can set a threshold. You can say that, well, you know, if the similarity is 0.4 or less, then call it, if the similarity is high, then call it part of the same recurring anomaly, and if it's sufficiently different, then call it not part of the same similarity anomaly. So the threshold basically is something that the user sets. Next slide, please. Then we do what we called the content-based search. So then we investigate the documents themselves and see whether or not those documents are referring to other documents. So in my picture here, D1 is referring to D2 and D4 refers to D6, D3 and D5 are not referred to, and so they're just kind of hanging out there. So this is, again, done by computer. None of this is done by hand. Next slide, please. Now, once you've done that, what happens is that you can develop a set of recurring anomalies. You can actually identify out of a corpus of reports a set of recurring anomalies that shows you basically what are events that are happening together. And we have a visualization system that perhaps you can see that shows you an expanded view on the upper right-hand side of the screen. Some documents have been linked together with other documents, and those comprise a recurring anomaly. Next slide, please. So the question is, does this thing work or not, right? And so we took a data set from the shuttle orbiter corrective action records. We took a subset of 333 documents. You might say, why that many? Well, because that was a good number. It was representative. But we couldn't ask our friends at Johnson to read 7,000 documents for us. And so we just took a subset of it. Once we had that subset, we asked them to take a look through it and say, please tell us where there are recurring anomalies. And it turns out that they found 20 recurring anomalies. We ran our system, which we call READS, which stands for Recurring Anomaly Detection System. We ran reads on the data set. Lo and behold, we found 39 recurring anomalies. So did it work or did it not? It's hard to say. Let's move to the next slide. So here's a breakdown. Next slide, please. So here's a breakdown of what happened. Of those 333 reports, 58% of them were tossed out by the read system as being not part of a recurring anomaly. 12 exact matches were discovered between what the experts found and what reads found. So 12 hits, perfect hits, which has been done by reads. 6 previously unidentified recurring anomalies were discovered by reads, which were then confirmed by experts. So we discovered some more things that the experts hadn't seen in the first round. One record was identified by experts as being part of a recurring anomaly and was missed by reads. So out of all those documents, we missed one document in linking it to a recurring anomaly. Now some might say, well, gee, that's great. You only missed one. Others might say, in fact, that's not so good because that one document might have been about the foam, or that one document might have been about a certain adhesive that's being used on the foam or whatever. And so you could imagine that perhaps we need to do some tuning here. For this application, though, it turned out that missing one document was okay. 5% of the expert recurring anomalies were separated by reads into more than one recurring anomaly. So that basically means that we took the documents, we grouped them together, and we got an answer. We grouped them in a different way than the experts did. So some might say, well, that's not so bad because at least you found all of the recurring anomalies. And then 8% of the reads RAs were combined 2 expert RAs into a single RA. So what that means is that we took 8% of the recurring anomalies that we had were combinations of recurring anomalies discovered by the experts. Next slide, please. So what have we done? Well, we've enabled the capability to find recurring anomalies in data sets, and in fact in multiple data sets. What I haven't shown you, though, is the ability to compute trends in that, and that's something that we're working on at the moment. We've enabled that technology. We haven't yet performed the computation. READS is a novel tool designed especially for this purpose of finding recurring anomalies. So again, we believe that if you just took a tool, a software tool, and you ran it on this data, you may find some recurring anomalies, but you may also not. It's not really designed for that purpose. And what we really wanted to do, in fact, in this study as well as in all the studies we do, we really wanted to do something that NASA needs. And so we heard about recurring anomalies from the NESC, and we decided we're going to build something that does exactly that. We've developed what we believe to be a robust platform to analyze and visualize the recurring anomalies so that people can actually interact with the system, say, you know, these are good recurring anomalies, these ones aren't so good, shuffle through the data, and basically give them an ability to deal with these massive sources. Next slide, please. Okay, now we've talked about text, and now we're going to switch from text to the analysis of continuous and discrete data, and we're first going to talk about the analysis of discrete data. Next slide, please. So here's the background, and we call our algorithm, by the way, sequence miner. So imagine again that you've got a large corpus of data, discrete parameters, let's say from 10,000 flights, and these flights are all stored on a database, and somebody comes to you and asks whether or not there are anomalies in the switching patterns. And so what we do is we developed an algorithm called sequence miner that mines through this data, it sorts through all of this discrete data, and it identifies typical behavior. We don't tell the machine what's typical. The algorithm automatically discovers what's typical. And then once it does that, then it goes and it takes each flight and compares it with what's typical. If something turns out to be far away from what you've observed to be typical, you call it an anomaly. And the question is, though, how do you actually go about doing that without encoding standard operating procedures? That's really the key. Next slide, please. So here's a little cartoon example again. We've got switches A through Q, I guess, on the top part of the chart. And here's, let's say, a typically observed sequence, ABC, DAD, DAG, FQ. Nobody needs to memorize that. It's just up there to give you an idea of what a switching sequence might be. The exampled observed switching pattern might be what's below. And what I did is I moved the GFQ from the very back, from the end of that sequence up to the beginning. Now the question is, can you do two things. First, can you figure out, given a corpus of data, remember given 10,000 flights, what that typical switching sequence pattern is? And then the second thing, can you develop a method to compare a specific flight against what's typically observed? Next slide, please. So, the outline of the approach is as follows. We rely on something called the normalized longest common subsequence. It's a mouthful, and what it basically does is it tells you how similar are two sequences by measuring the longest common subsequence in the data set. This is a pretty quick method that we've developed. It analyzes 7,400 flights in about 6 minutes. Sequence Miner discovers switches that are absent in an expected sequence position, switches that are inserted in an unexpected sequence position, and switches that are out of order from what is expected. So those three things Sequence Miner can catch. We've tested it on toy data, and we've also tested it on real data, and I'll show you that in a moment. We also can describe why a particular flight was called anomalous, which is, I think, important for adoption in the aviation community. We need to not just say, this flight's anomalous, but we need to be able to say why. And we need to put numbers around it, and we try to do that. Next slide, please. So we rely on something called multiple sequence alignment. And so, again, going back to doing your own research, you'll find that MSA is used in bioinformatics to compare DNA sequences of organisms descended from a common ancestor. So that's interesting because we can rely on that sort of guidance from bioinformatics in order to develop this algorithm. One key difference, though, between what we're dealing with here is we've got let's say 100 switches, or let's say 1,000 switches that we're dealing with, and in bioinformatics they have 4. And so that's one important difference. We can search for mutations, which is basically those insertions and deletions that I was describing, and then identify where something deviated from the norm. Next slide. So in order to get this really to work on the aviation data, we also needed to incorporate operational information. And we did that in two ways. The first way was to incorporate switch weights. So we had an expert pilot go through all of the parameters that we had, and he tagged some of those parameters as being important and some not being important. And we, in fact, used the Likert scale. So we had a scale. He said that the higher the number, the more important the switches, the lower the number, the less important the switches. Somebody could argue with that particular weighting that he gave. In fact, that happened, so we can reweight them, and we can do it again. So we can incorporate expert information on the fly. We can also ignore switches that happen in a 1-minute time interval. So you could imagine that certain switches, it doesn't matter if you press switch A and B or B and A within 1 minute. Let's just say it's okay. So we can have an arbitrary equivalence class that's built basically at a 1-minute time interval. And so with those two things, we've incorporated some operational information. We always believe, though, that by incorporating more operational information, our algorithms will work better. Next slide, please. So we started off with 7,400 flights in order to test this system, and it consisted of about 1,000 primary and secondary binary switches. Primary switches are the switches that the pilot actually flips, and the secondary switches are kind of the reactions of the airplane back to the pilot, so changes in actuators and things like that. So we were left with about 111 primary switches, and we also down-selected the data to about 2,200 flights so that we could analyze landings at a specific airport rather than looking at all airports, because it turns out that different airports might have different landing procedures. We did actually both. We looked at the 7,400 flights as well as the 2,200 flights. Then we took the top 13 anomalous flights that our system Sequence Miner found, and we analyzed them. We asked the expert to look at it and say, what did we find? Which is really key here. So 5 were judged to be bad data. Now that can be good news and it can be bad news. It can be good news for us because that's certainly anomalous. Bad news maybe for the people that are recording the data. Maybe they have to go and fix something. 3 were judged to be normal, and 5 were judged to be what we call operationally significant. That means that in the pilot's estimation, he thought that what was discovered by Sequence Miner was actually anomalous and it had some operational import. So that's, I think, of interest. Next slide, please. So here's a chart that shows you what happened on one flight. I'm going to take you through a couple of these charts. So Sequence Miner discovered anomalous presses of the igniter switch. So an airplane's coming in for landing. On the top, the chart shows you the altitude as a function of time to landing. Airplane is coming in for landing, and the pilot presses that igniter switch, which is in red, a whole bunch of times as that airplane's coming in for landing. The expert said, well, the pilot switched igniter on and off at atypical times, and this could be an indication of engine malfunction. Obviously, we don't know what was going on, but we do know that Sequence Miner found something that the pilot deemed to be anomalous. Is it operationally significant? Well, yeah, if the engine was actually having an anomaly associated with it, yeah, there could be something here. Could have been bad weather. There could be many explanations. We're not trying to explain why. We're just saying we found this thing. Next slide, please. So Sequence Miner discovered anomalous engagements of the autopilot. This is a different flight, by the way. So here the airplane is coming in for a landing, and in about 16 minutes before touchdown, you see the pilot flipping that autopilot switch. Now, I'm not a pilot, but in speaking with many of them, they say that what happens when sometimes is that a pilot can experience mode confusion. I'm not a scholar on mode confusion, but my understanding of it is that the pilot is flipping switches trying to figure out what configuration is the airplane in. And so that's happening a lot at 16 minutes before touchdown, 4 minutes before touchdown, and 1 minute before touchdown. That corresponds to the bars that you see on the screen. So the expert said, well, this looks like the autopilot was used too many times, and it might be a case of mode confusion, which is actually one of the things when Irv came to me with this problem about a year and a half ago, he said, you know, it would be really nice if we could design a system that would find mode confusion. Maybe this thing has actually found it or not. We have to do more testing, but it seems plausible right now. Next slide, please. Sequence Miner discovered anomalous usage of speed brakes. So here the airplane's coming in from 30,000 feet at about 20 minutes before landing, and the red bars indicate where the pilot pressed the speed brakes. So the expert looked at this and said, you know, Sequence Miner might have found an overuse of speed brakes. And it could be in what's called a high-energy approach. That means the airplane is coming in too high, too fast. And so this may have some operational significance as well. Next slide, please. So again, what are our innovations? What has been accomplished? Well, Sequence Miner is a fast and reliable system to learn typically observed switching patterns from large volumes of discrete data. Why do I say fast? Well, 7,400 flights in 6 minutes. Why do I say reliable? Well, because every time you run it, you'll get the same answer. Now, some of you might think, well, that's great and that's obvious, but it turns out that many machine learning techniques that are out there, hidden Markov models and so forth, don't give you the same answer every time you run it. For this problem, we had to develop an algorithm that would actually give you the same answer every time you run it. That's why I say it's reliable. It outperforms other algorithms in terms of speed, and it discovers operationally significant events such as mode confusion and high-energy approaches. Obviously, we have to do much more work with this to understand how it's working and to see whether or not we can mine more information out of it, incorporate more operational information. That all goes without saying. Let's move on now. Next slide, please. Now I'm going to give you a few slides that talk about some work that we've done on shuttle systems, and I'm going to focus on Columbia and on the wing leading edge of the shuttle. Next slide, please. Here, instead of dealing with discrete data sets, as I was doing before, and instead of dealing with text, as what I was doing at the very beginning of the talk, here I'm going to talk to you about mining and understanding continuous data streams. Frankly, at NASA, a lot of data that we have is in continuous format. A lot of the science data is continuous data. A lot of the aeronautics data is continuous, and it turns out in the space systems, a lot of the data is continuous as well. So we developed a system which is called Inductive Monitoring System, IMS. What IMS does is it monitors all of the continuous data that you give it. Not just one signal or two signals, but you could give it 30 signals, 50 signals, and so forth. You could give it as many signals as you want. And it builds an internal model of what's normal. So that means that you give it what you say is normal data. You've got to say it's normal. You give it normal data, and it develops this internal model. Now, just like with Sequence Miner, what happens is that new data comes in, and it's run through, and it determines whether or not it's seen this before. If you've seen it before, you say, okay, it's not anomalous. If you haven't seen it before, you say it's anomalous. What we do is we actually calculate a degree of anomalousness that tells you how anomalous is the particular signal that you're looking at. That's the monitoring phase of IMS. Next slide, please. So we're going to now look at STS-107, which is the last flight of Columbia. And I'd like to point you to some details about this particular study that we've done. IMS method can help identify subtle but meaningful changes in system behavior. It can do that. We've seen it do that many times on different sorts of data sets. Now, when you take STS-107 data and you compare it with the previous flights of Columbia, it turns out that you can see some anomalous behavior on those leading edges of the wings. I'll show you those charts in a second. So it could be that such a system like IMS could help with understanding if something is deviating from the norm. Next slide, please. So in STS-107, this chart hopefully shows you the positions of certain sensors on the wing. And these sensors are measuring basically the heat that's coming on the wing, and obviously you'd like that heat to be low. Now there's multiple sensors here, and it turns out that if you monitor any one of those sensors, they'll probably stay within bounds. I haven't looked at that data myself, but I understand from the people at Johnson it stays within bounds. Next slide, please. Now, when you take IMS and you run it on that data set, on a nominal data set from STS-93, which is a previous run of Columbia, you'll see that the IMS produces two signals, which is basically that anomalousness score, and that score is actually below a threshold that we've set. And so everything looks fine here. Now let's switch to the next slide. STS-107 has a different profile. So what you'll see here is that after launch, we're dealing with about the last 8 minutes of data, or the first 8 minutes of the launch data, I should say. What you'll see here is that everything seems normal, and then all of a sudden there's a foam impact, and we know that not from this particular data set, but from the cameras and from the other evidence that we know of. Foam impact occurs, and what does that IMS start telling you? Well, something is different. In fact, that pink curve starts to show that the left wing is somehow deviating from what you've seen before. And in fact, as time progresses, 3 minutes afterwards, as time progresses, that deviation grows and grows. So what this tells you is that the IMS system retrospectively can look at that data and see that there was a problem on it. Next slide, please. So the innovation is that the IMS system can learn a model from nominal data and then can take data and do a comparison. We're using currently IMS to detect wing impacts in support of STS-121 and recently on STS-115. And we've been working very closely with our friends at Johnson in order to make sure that our algorithm is matching what their needs are. And we're also going to be deploying IMS on console at Mission Operations Directorate at JSC. We've developed another algorithm called ORCA, which I haven't gotten into during today's presentation. I have a few slides in the appendix if you're interested, but we use that algorithm for doing prognostics on SSME. Next slide, please. So in conclusion, I've taken you through a lot of slides here, a lot of discussion about three basic data types: text data, discrete data, and continuous data. So we call this heterogeneous data, and we're trying to develop algorithms that will transparently mine such data and uncover safety anomalies. That's our aim. We're trying to enable the automated analysis of the distributed national ASAP and FOQA archives, and we believe that these methods are comprehensive in the sense that we're doing monitoring, we're doing detection, and we're also doing analysis of system anomalies. Next slide. So where do we go from here? Well, we've got to do more of it, right? We need to be able to have a better understanding of what's going on in those systems. We need to incorporate more expert information. We need to do more comparisons with what's known, and we need to make those systems more robust. We also need to develop more prognostic technology. We have a little bit of it, but we need to do more of that. In other areas, one thing that I'm doing with a colleague at Google is developing a new book on text mining, because I believe, as does the publisher, that this sort of work that we're doing is new and could have broader implications beyond NASA. And so this is a book that I'm working on with Chapman and Hall. I just got, 2 days ago, I got an announcement saying that they accepted the proposal that we wrote. We're also going to be conducting a text mining competition, and I'm kind of excited about this because it gives a method of giving the larger public ASRS data, which is public, and asking them to do a good job at classifying data. So those of you remembering your grad school days, you're going to know that you're going to get this data and mine it and try and get the best answer. It's a competitive situation. Whoever wins gets some sort of a prize, and it should be a lot of fun. Probably those results will also be comprised into a book. Another thing that we're doing at NASA Ames is developing a data mining consultancy. So this is going to be a group of people sponsored by the NESC that is going to go forward and help different centers, NASA centers, help them in understanding some of the data mining technology, maybe get some of that data, bring it to Ames if possible, mine it for them, and then provide the answers back, and then provide them the technology so that they can do it themselves. And so this is the notion of a consultancy that perhaps could be of value. We have to try it out. We've never done anything like this before. Certainly in my group, we haven't done anything like this before at Ames. And so we hope that this would be something that would be useful for the agency. So in conclusion, I'd really like to thank Dr. Porter for inviting me and Irv to speak with all of you today. It's been a real pleasure, and I'm very proud to be representing the people in my group at Ames and also to be talking to all of you here in this historic hall. So with that, I'd like to have Irv come back and join me at the seats, and we'll take some questions and answers, hopefully provide some answers for you in the viewing audience.
Hello, I'm J.D. Harrington, and I'll be moderating over the question and answer session. If you have a question, please raise your hand and state your name before you begin. I also have been told we have the ability to take questions from some of the centers as well. In the meantime, I was able to, I had some emailed questions to me to get things started. The first one has to do with proprietary, intellectual, and personal privacy data. How does your data manipulation and data mining affect these issues?
Yeah, that's the key question because as you look out at the literature, you'll see that data mining has become a field where privacy and privacy preservation is of key importance for obvious reasons. And so we need to make sure that as we build our systems, we're cognizant of that and in fact enforce privacy-preserving algorithms. So in this program, we're actually working with a professor who is one of the experts in the field of privacy-preserving data mining, and we're writing and developing new procedures for enforcing the privacy constraints. It turns out that you can actually build algorithms that respect certain privacy constraints. So you don't have to take all the data from all those archives, ship it all the way back to NASA Ames, and then do some sort of an analysis there. You can actually do these things separately, and you can actually do these things in a way that you never have to bring the raw data back, not even one drop of it. And so what this does is it gives you the ability to get an answer out of this distributed archive, but without actually bringing the data back, and therefore you end up preserving the privacy of all of the airlines.
And
thank you.
If I may add to that.
Absolutely.
As I mentioned, there is a constraint on the National Archives where we must not have any access to private information. So we're relying on techniques like this to protect the identification of the sources of the data.
I haven't today described to you the privacy-preserving algorithms, but there's quite a literature that's developing on it, and we're trying to partner with some of the key people and organizations that are at the forefront of it so that we make sure that we're doing the best job that we can do.
Okay, thank you. The next question I have here before we go out to Dryden is, what is NASA's long-term plan for ISS? Will NASA go on to implement and maintain this database after you've finished developing the data mining techniques?
So was the question regarding IMS?
ISI?
ISI.
Well, we were going to be discussing this afternoon, in fact, the future plans for this entire program. At the moment, we're discussing collaboration with the FAA on how this should proceed. Obviously, while NASA has been responsible for the operation of the archives during the demonstration mode, we have completed that phase, and now we have to start thinking about transitioning to a more permanent organization, and that will be part of the discussion just this afternoon.
Okay, we now have a question from Dryden.
This is Rod Bogue at Dryden. I have a question regarding, continuation of the question regarding privacy. Seems to me that the keeping the data at the various airline facilities suggests that the airlines are somewhat concerned about that. I know they are very concerned about the privacy of the folk with data. I'm wondering if you see this particular structure for storing data to be something that will persist, or do you think eventually you'll put this all in one large database at one particular location?
I'll field that one. No, I don't think the climate is ripe for considering aggregating the raw data anywhere. I think the notion is a distributed national archive of data, and the data will be protected by the owners of the data.
And I would add to that by saying that I don't think that we will have the need to do that. So there's a question of policy, and there's also the question of need. And I think that from the need standpoint, the technology needs to be developed to do mining of data while respecting privacy. It has to be done, and it is being done, and we would like to take advantage of that so that we can maintain what the airlines want to have as far as the segregation of their data. We would also like to be able to understand some safety implications from it, but I don't think that there's actually any difference between those two things. I think we'll be able to understand safety implications from the data while keeping it distributed.
Okay, I have one more question. Anyone from headquarters have a question? Okay, come down here to the front.
Yeah, that's a very nice question. Every Monday morning, almost, Irv tells me that this is something that we have to be working on. I think it's of critical importance, and I know that he would agree with me. You're right. So it's great to be able to mine one kind of data, mine the other kind, and somehow hope that your mind can come up with a hybridization of those two things. What we're trying to do, though, is use a new capability that would mine these two things together so that what you find out from continuous data and what you find out from discrete data can be used either to do corroboration or for discovery. So that means that new algorithms would have to be constructed. So again, going back to kind of the mathematics behind all of this, there are ways of representing continuous data as discrete and discrete as continuous and so forth, and you can do all of that. But what we would really like to do is keep the data in its native form, keep discrete, discrete, continuous, continuous, and write the algorithm so that they can deal with it. And then once you've done that, then you somehow need to be able to determine what is anomalous and what's not. So this is a problem that's going to be, in my opinion, addressed through the use of some optimization techniques as well as through the use of some new machine learning and data mining capabilities.
May I add to that, please? Thank you for the opportunity to answer that question. Because as you know, we have developed capability for identifying automatically atypicalities in the continuous data. The focus was continuous data, and I confess to driving it that way because at that moment it was the low-hanging fruit. And we have a capability called the Morning Report that has been patented and has been demonstrated to find anomalous situations, atypicalities in conventional flight performance data. But that isn't the answer. If we're ever going to find answers to things like mode confusion, we need the sum of both. And that's why we have people like these geniuses working on it.
All right, thank you. We have one more question here, and the question involves, can your data mining techniques be used in other venues or enterprises, such as healthcare, homeland security, or possibly the FBI database that was in the news about a year ago, fighting terrorism?
Yeah, certainly data mining can be used for security applications. Previously, about a year and a half ago, I was on the Homeland Security Presidential Directive 11, HSPD 11, where we discussed the usage of some of these technologies for Homeland Security purposes. It can indeed be used for a variety of other applications like healthcare, business. Before coming to NASA, I used to work on building algorithms for doing forecasts on Wall Street, for doing online advertising, and for cars and so forth. It can be used everywhere. I like to say, if you've got data, we can mine it, is kind of my attitude about it. And I think it goes to say, I say that because this world is filled with data. And isn't it interesting to come up with algorithms that can actually go through and give you some understanding of what we're seeing? We've talked a lot today about aeronautics data and engineering data. But on the other side, as far as scientific data goes, the data volumes are incredibly enormous. And we need to develop these capabilities. And one of the reasons I'm at NASA, one of the reasons I'm proud to work here, is because we're in a unique situation to actually get that data straight from the satellite and mine it and determine things about what's going on in our planet, what's happening in the geosphere, what's happening far, far away in the galaxies.
And also, the analysis techniques and the data collection techniques should be designed together, because sometimes we are collecting data and then we have difficulty analyzing them.
All right, thank you. I believe we have one more question here in the headquarters audience.
Thank you. This is Andy Muir with the FAA. I'd like to learn a little more about the Mariana technique. It seems to be a technique that would probably be more effective with a larger volume of data. And I was wondering if you have a sense of, is there a minimum number of reports on which it might be effective? For example, the current DNAA archive was mentioned to include, I think, 10,000 reports. And part B of the question, I guess, is could the Mariana technique also be enhanced by some of the NLP-type concepts, such as thesaurus of terms that are specific to aviation safety?
So I'll answer the part B of the question first. So what we've shown in one of the slides is that the Mariana technique, without using NLP, so this is dealing with straight raw data, raw text, compared with using an SVM, where you're using NLP techniques. So that's the comparison, okay? Mariana, which is the souped-up, hyper, really cool SVM package that we've developed, and then there's the standard SVM package. Both of them are getting data. One gets the raw data. One of them gets the data which is processed through NLP. It turns out for most of those categories, they're very comparable as far as their performance goes. In fact, in some cases, the Mariana technique does better than the SVM technique using NLP. So in other words, Mariana is better than NLP plus the support vector machine. We've seen that. Now, that's not a definitive statement on all text data sets. It's just a statement about that specific data set that we're dealing with. Now, the first part of your question regarding the frequency of anomalies, this is really at the crux of a lot of issues that we're dealing with. The number of reports that are available and the frequency of certain anomaly categories. So what we've found is that the Mariana technique can actually work quite well with relatively skewed distributions. So when I say skewed, I mean you might have in-class representation of, let's say, 5% or 2% or 1% and 99% or et cetera in the non-class situation. You're trying to do a discrimination there. You have to do some pretty fancy things in order to deal with it, but some of the results that we have indicate that we are able to do it. It needs to be improved, though, and the best way to improve it is to get more data. We always want more data, but we understand that people can't produce more data. And so we're developing systems based on the theory of active learning that can actually take some reports and kind of estimate, kind of guess. The system can guess which category it goes into, and then a human being can say, yep, you're right, no, you're wrong, no, you're wrong, no, you're wrong, et cetera. update the system, and then it tries to learn that way. So this is pulling on the theory of active learning from the field of machine learning. So the skew class distribution is something that is critical in dealing with this sort of data, because some classes are highly skewed, necessarily so, and other classes are very frequent. And so to build algorithms that can deal with both of these kinds of situations is challenging and a good deal of fun for us.
And Andy, for aviation, as you well know, is particularly challenging because in all cases we're dealing with very rare events. These are rare incidents. Some are more rare than others. And it's the really rare ones that bring the challenge, and sure, it doesn't happen very often, so there are very few data.
And one more data point that I would give you is on the DNA categories that you're asking for. We did an analysis across 23 DNA categories of taking ASAP data, mapping it into those 23 categories. And what we found is that the median false positive rate was on the order of 10%, and the median true positive rate was on the order of 90%. And so that means that across those categories, about half the time we're doing quite well, if you believe those numbers are good. And then there are some of those that are doing worse off than the numbers that I quoted. But for those categories, in many cases what we're finding is that they're very, very broad categories. They're called, for example, non-adherence to non-adherence categories. I don't remember exactly the definition of it, but they're very broad, and so it's difficult to discriminate whether something falls into that category or not.
In the DNA master list, there are 32 events. We've not done badly on 23. We've not done quite as well on the other 9. But he'll do better.
All right, thank you. I believe we have one more question here on the corner.
Yes, Vicki Chris from Fundamental Aero. You talked about the evaluation of national data. When you move out to looking at data mining international data, will the influence of our cultural differences have any impact on your processes that you're currently using?
Every culture speaks in a different language. Even in this country, the language used in the pilot reports is not the same language that is used in the maintenance reports, is not the same language as is used in the accident reports that come from the NTSB. And we've already found that out. We recognize the differences in the languages, much to our dismay. So, yeah, most certainly, if we try to go up international, then at least the language differences will enter into it. You can't design a system like this without understanding something about the language. But of course, if these wonderful techniques that are largely based on statistical methods apply, then there is a generation of a model in the process. So we can learn from given enough models in a language of that culture.
Remember that the fundamental quantity that we're dealing with in the text mining work is the bag of words matrix, which just has documents and it has terms in it. And so we haven't demonstrated what will happen when you take French or German or some other language and import it into this system. We haven't demonstrated that. But fundamentally, the mathematics behind it doesn't change. And so that gives us some hope, but we have to demonstrate it yet. Right now, all I can say is that I'm hopeful.
But I assure you, if you can deal with the language of a typical pilot's report, you can deal with anything.
All right, I think that's about all the time we have today. I'd like to thank you all for joining us today, and specifically on behalf of Dr. Lisa Porter and Dr. Jaewon Shin, thank Dr. Stadler and Dr. Srivastava for joining us today. If you'd like more information about aeronautics programs and that, you can go to our website, www.aerospace.nasa.gov. Thank you.